3.2 from the textbook goes into exponential decay, for example, half-life. Before we get into exponential decay, let's talk about growth. An example of exponential growth would be the human population. The human population shows a pattern of growth in which each term, so maybe the population in this year versus the next term, maybe the population next year, would be multiplied by a constant amount that's greater than 1. Because it's greater than 1, it will grow faster and faster. But if we're talking about exponential decay, that's where you have an example, maybe an isotope, where you have a certain amount of a chemical element and it becomes smaller and smaller in amount over a certain amount of time. And that's because you're multiplying by not a number that's greater than 1, but instead a number between 0 and 1. That means that your amount is going to become smaller than the previous amount. Let's take a minute just to address half-life. So half-life is the amount of time that it takes for something to become half of what it is. There is a formula that helps out with these types of questions, and it's right here. Okay, so we have A0, which represents the initial amount, and that's because the 0 is for time. When time equals to 0, what is the amount of whatever we're talking about? Now A is the final amount that we're trying to look for. So after a certain amount of time, how much of it is still present? This half is the rate, and it's a half because we're talking about half-life. The T up here represents the amount of time that you're looking for, and H represents the amount of time it takes to become half of what it is. So in other words, the half-life. Let's try a question. The half-life of radium is 1,620 years. If the hospital initially had 10 milligrams, how much will they have after 50 years? So what I like to do is I just like to write down all of my givens on the left-hand side. So first of all, they told us what the half-life is. It's 1,620 years. Now I also have the initial amount. So the initial amount, which is A0, is 10 milligrams. They're asking for how much. So how much are they going to have? That means they're looking for the final amount. And they gave you a certain amount of time that they're looking for. This is our T. You always want to make sure that your half-life and your T both are in the same unit. Okay, so in this case they're both in years. We're just going to plug everything into our equation. So here's our equation. And then we're looking for A, so our initial amount was 10. 1/2, and then we have 50 over 1,620. Never ever multiply the 10 and the half together. It's a common mistake. Remember, you want to do BEDMAS. So do 1/2 to the power of 50 over 1,620 first. I'm just going to grab my calculator and do that very quickly. So I'm getting 10 times about 0.9788. Now there's a bunch of numbers afterwards, but I don't want to write them all in. I'm going to just tell people that it's been approximated, and that's what that little dot is for. So this is an approximate answer. I'm going to keep all those numbers in my calculator though, and then just hit times 10. So after 50 years, it looks like I have about 9 point, and we'll say to maybe 1 decimal place, 8 milligrams left over. Now does that make sense? I mean, initially we had 10 milligrams, and after 50 years, which is a long time, we still almost have about 10 milligrams. And it should make sense because, take a look, it takes such a long time to become half, so about 5 milligrams, so 9.8 is reasonable. Let's take a look at another question. We have strontium 90, so the 90 has no significance, it's just what the name of the element is used in machines that control the thickness of paper during the manufacturing process. Strontium 90 has a half-life of 28 years, so why don't we write that down, 28 years. Determine how much time, so that means we're looking for time, has elapsed if 1/4 of the strontium-90 sample remains. That means they must have given us A and A0. But it doesn't look like they really did. They just told us something about a quarter. In this case, you get to decide what you want as the initial amount. So let's just say I decided, okay, the initial amount is 1. It's just an arbitrary number, because then the final amount has to be a quarter of that. So a quarter of 1 is just 1/4. So for example, if you decided that you wanted to start off with 100, then you'd need to make sure that your final amount was a quarter of 100, and that's 25. So it just doesn't really matter what you put as your initial amount. I'm just going to put 1 and 1/4. Then you're going to put everything into the formula. So you have A0, 1/2, T over H. And this is 1/4, 1, 1/2, T, which is an unknown, and that's all divided by 28. All right, so how do we solve this? First thing you're going to do is you're going to divide out this 1. Now, when I divide out the 1, nothing's really going to happen, so I'm not even going to write that down. I'm just going to rewrite without the 1. In order to solve for the t, you're going to need to make sure that you have the same base. So 1/4 is just a half squared. And I have my other base, which is also a half, t over 28. This indicates that their exponents must be the same. Now I can solve for t. I just cross multiply. So t is equal to 56. Now taking a look back at the units, we're talking about years. So 56 years for the strontium-90 to become a quarter of what it is.